example why we need to do the inverse Laplace transform, and then we will look at how we use this on the circuit. So we're going to start chapter 13 if we have time. I'm not going to use the whole time to talk about these topics, but I want to start with, I'm going to start with this topic. Okay. For the past exam, a lot of people ask me about, well, what is the unit step function? Okay, and then people ask me, what is the impulse function? I thought you guys know this already, but I wanted to let you know some of the important property about these functions. These functions are what we call the singular function. It's singular because it's not differentiable. They have some like a piecewise character. They're only valid at a certain time. So there are three different functions. They are closely related. Start with the unit step function. We use unit step function a lot. When you hear about unit step function, meaning it's a unit, which means the magnitude is equal to 1. Step function meaning it will change at a certain time. The time doesn't have to be 0. If you have t minus 2 in the parentheses of this unit function, it means when time equal to 2, then inside of the parentheses equal to 0. When that equal to 0 and or greater than 0, it will become 1. So that is what a unit step function. The one that I show you right now on the screen is a standard one. It's just this t. You only have t in the parentheses to represent what the function is depends on. And mathematically to express that is the one on the square that tells you use of t equal to 0 or 1 depends on the time. So time is greater or less than 0, give you that situation. That is the unit step function. Okay. Again, this works on many different fields. Okay, if you are not has to be like double E, but mechanical, all kind of things that we specify this to simplify our work. Now in the circuit that we know how you going to use this. You know this because we can use this to simulate switch. And it simply tells you at this, like this standard phone, the time equal to 0, you're going to switch on or switch off. If you make the shift in the time, meaning you make the t minus 2, that simply tell you at time equal to 2 seconds, I'm going to switch on. So that is a simulation of the switch. The second important function we didn't pay a lot of attention on is the impulse function. Now, impulse function is important for sampling. I kind of tell you the sampling idea. I didn't like fully explain how the sampling is. So the sampling is if you have a signal, it could be any kind of signal, and you wanted to get the value of some specific time, like instantaneous value, then you can multiply that function with an impulse function. When you multiply that function with the impulse function, and you look at the impulse function, the middle one, the delta t, that one only have a value at time equal to 0. But you can also shift it. Similar to the unit step function, if you shift it, meaning I'm going to only get the value at that specific time. So for the rest of them, I make it 0. And so that's why we call this as a sampling function. The sampling function only pick the value at that particular point. And because it's a unit impulse, so the total area under the arrow, you can think about the arrow is a very narrow, small time period. And it has the magnitude. The magnitude is almost go to the infinity. However, if you count the area under that, the area is 1. So that is what we call the impulse function. And we use that to do the sampling. But there are a lot more way that you can use the impulse function as well.
Wait, quick question. Why was the area 1?
The area under this impulse. So over here, if I If you blow up like this part, this is the change of time. This is a very small change of time. And the unit, if that's a unit impulse, meaning the total area under this one goes to almost like infinity. But if you count the area and the small change of time with the amplitude go to the infinity, and that area under this is equal to 1. So that's what the impulse function is. Okay. The third one is called the ramp function. The ramp function. The ramp function, the symbol is r sub t. The ramp function, you look at the function, it's just like a slope. It's just like a slowly ramp up. And if this is a unit ramp function, meaning the slope is equal to 1. So the slope is equal to 1, meaning it's a ramp function. Okay, and because it's a 1, so you can see the 1 on the y, 1 on the x. So that's the unit ramp function. The ramp function also have a time where you have the value, time equal to 0, or you can shift it as well. When time is greater than 0, then the function itself is just the function of time. Now, I said these three are related. So how do they relate? If you take the slope of this, that starting from time equal to 0, the slope of this is always equal to 1. And that is simply meaning the use of t is the slope of this ramp function. And what do we mean by slope? The slope meaning differentiation. So you have a ramp function, you take differentiation, that differentiation is the unit step function. So differentiate a ramp function, give you the step function. If you take the slope of this, and you're going to get the impulse function. So they are like a differentiation or integration. So one way go to the differentiation, the other way go to integration. Just like when you do the 130, the physics 130, when you study the kinematics, that we have a position, velocity, and acceleration. So if you know the velocity, you differentiate, you got acceleration. You integrate, you got a position. It's very similar to this. These three functions are related in this way. Now, you might wonder why we wanted to introduce these. Not only they can simulate the circuit, but they can also help you on finding the Laplace transform as well. Just one example over here. We have a pulse train like this. Very simple, like a pulse, starting at 2 and end at 5. The rest of them is going to be 0. We kind of show you this example before. If you wanted to represent this function in the u sub t, and you know you can represent this one is a u of t minus 2 minus u of t minus 5, right? So that is one way you can find the Laplace transform by simply write down what is the function of those basic functions that you can use to represent this graph. And once you have that, you can use the table. So here is the table, and this table 12.1 to 12.2. These two tables can help you to find the Laplace transform or inverse Laplace transform. If you want to find the Laplace transform of this, let me change to my pad so I can write down something.